In the last video, we talked about electrostatic potential. So today we are going to take a situation wherein we have a source charge and we want to find what is the electrostatic potential due to a point charge. So we take this example. Suppose we have a point charge, a source charge here, Q. And we have a point P here. And we are interested to find, because of this source charge, and let's take this source charge as positive, right? So it creates a condition in the space, it creates the influence. We are interested to find at this point P, what is going to be the electrostatic potential expression with a given condition that this charge is at a distance of r from this point. Now, we'll talk about the very basic definition of electrostatic potential, and then we'll figure out how step by step we come with the expression for the electrostatic potential. Well, so if we join these 2 points, suppose here, so we know because of this at point P, there is electric field at point P. With all these given quantities, we know what is the electrostatic field at E field at P. With this given condition, this comes out to be 1 over 4 pi epsilon naught Q over R square. And we multiply this with a unit vector R. So if you indicate this as point O, so we are saying that this point OP vector is R vector, and it's the unit vector along is R unit vector. So we have multiplied this magnitude with the unit vector to get E field at point P. Now recall the definition. The definition of electric potential was, what is that work done in bringing a unit positive charge? So suppose I take a unit positive charge, 1 coulomb. A unit positive charge from infinity to this point is what is the definition of electric potential. So work done against, or work done by the external force against the electrostatic force in bringing a unit positive charge from infinity to this point. If we are able to determine this, then we are able to figure out what it is. Okay, with this given condition, suppose this electrostatic field is indicated here, it is going radially outward. So from the definition, we know that this force external should be equal to, this force external exactly should match with the electrostatic force with this Q is going to exert on this. So electric field definition is this electrostatic force per unit charge. So if you want to figure out what force of external is required so that there is no acceleration of the charge, it's going to match exactly with the electrostatic force exerted by this source charge Q to a test charge 1 coulomb, and that is equal to, since it is 1 coulomb, so if you equate this to the definition of electric field, we can write this should be equal to negative of 1. Why negative? Because negative is the electrostatic field force that is there, which is in opposite direction to the external force. So the work done, this should match with this. So this should be equal to 1, which is the charge times this times the electric field strength, whatever is the electric field, magnitude of the electric field. So we know this force external should be equal to the electrostatic force exerted by source charge Q to this test charge, but this should be equal to negative of force external. Force external is going to bring that force you would exert to bring that charge, do the work against this. So if you want to write an equation, it should come minus the electrostatic force. And we know this electrostatic force is if you divide by per unit charge, test charge, this comes out to be electrostatic field. So therefore, electrostatic field is equal to Q times whatever is the force, and this force here is negative of what it is, right? If you equate this with the external force, and if you multiply this so force per unit charge, right? So therefore this force is equal to Q times E. If it equals to Q times E, so that's what we are writing here. We are taking this test charge. This test charge is Q naught. Q naught is the test charge. We are taking unit positive to match on with the definition of it, right? So these were just for you to know how this relation comes. So this is what we are getting. So now we have related this force external with this one. Now if you want to find what is the work done, right, work done by the electrostatic field. So suppose we take the infinitesimal small, the direction dr against towards radially out towards where the electric field is pointing out. If you take that dr, so this dw is going to be equal to what? This dw is going to be equal to force dot dr. We know that any force, when you work done, force dot dr, it's a dot product, and we know that this is this. So this we can write conveniently, we can write this is equal to E dot dr. So this dw is essentially coming out to be negative of E dot dr. And what is the angle between E and dr? It's going to be 0. So therefore we can write dw is equal to, we'll take the minus out and we'll operate this, magnitude of this, magnitude of dr, and cos 0. So cos 0 is 1, and now we got just E dr. So therefore by definition, this work done against the electrostatic field, so therefore potential at P should be equal to, if you integrate dw, and this means that integration of this from where to where? From infinity to the point R, and it is E, magnitude of E dr, magnitude of dr. Well, this is what we get. If we are able to integrate this, we'll be able to get the answer. So let's continue here. We already know what is E, right? So electrostatic field is 1 over 4 pi Q over R square. So therefore we get Vp, which is the potential, is equal to negative of integration Q, or right, 1 over 4 pi epsilon naught Q by R square dr. Now everything else is constant except for the R, so we pull it out of the integral sign. So therefore we get this electrostatic potential is minus 1 over 4 pi epsilon naught, and Q is also there, so let's put it Q here, and integral 1 over R square dr. So we'll put our limits here. It's infinity to R, it's infinity to R. Now if you are going to integrate this, the result is 1 over R, so we'll write it minus Q 4 pi epsilon naught. So if you evaluate this integration, it's going to be minus 1 over R, and this is how we evaluate the definite integral. Now this minus, you take it out, so minus and minus would become plus, so therefore we are getting Vp is Q over 4 pi epsilon naught, and here we get 1 over R minus 1 over infinity. So 1 over infinity goes 0. So we are left with, therefore, we get Vp, that is the potential at point P. So there's no place to write. I'll just rub it here and write the result in this way. So we get R in the denominator. So we are able to calculate what is the potential at point P because of this point charge Q, right? And we get it is Vp is equal to Q over 4 pi epsilon naught R, and we know this electric potential is a scalar quantity, and we also know what is the unit, SI unit of this. So this is how we proceed with step by step, and we are able to figure out what is the electrostatic potential. In the next video, we are going to take dipole, electric dipole, and then we'll able to figure out what should be the electrostatic potential at different locations because of electric dipole. So watch the next video. Thank you.